Okay, so last time we talked about expectation and we went through some properties of expectation. And this time we're going to talk about variance and standard deviation, which is another related measure of for random variables. So the expectation is intuitively, it's where what we expect. It's roughly the location of where the random variable should be expected to be. And the variance is a way of measuring, well, about how far off do we expect our actual observation to be from what we expected it to be. Okay. So we're going to motivate the variance with a good way to understand it, to where the variance comes from, is with the following prediction problem. So suppose that we have a random variable. So we have a random variable called x. And for technical reasons, we're going to assume that the expectation of x squared is finite. Okay. We'll see why. But suppose that we want to predict a future realization of x. So we want to predict and so we want to come up with the best predictor of a future realization of x. In the sense of minimizing what's called the root mean squared error. We abbreviate as RMSE. Now, what is the root mean squared error? So the root mean squared error for a prediction. So if we predicted the value C, the root mean squared error is defined as the square root of the expectation of x minus c squared. So what we mean by, so think about what this is saying right here. Ignore the square root for now. The square root is, in some sense, well, we don't need to worry about that right now, but what we're trying to think about is, okay, we're essentially saying, well, you need to guess the value that x is going to be, and your guess needs to be good in the following sense. So what you're going to do is you're going to guess some number x, c, and the penalty you get will vary with the value of x that we observe. And it varies in this quadratic fashion. So the farther out you go, right? So if this is x, then this is x minus c squared. The farther out you go, the bigger it gets, and it gets bigger and bigger, right? It goes up faster as we go farther out. Now, and so that's your penalty. And what we want to choose is, well, we can't predict with certainty the value of X. This is why we talked about expectation, which was X is a random variable. It will vary, but we have a measure in terms of the expectation to nail down a specific, give us one measurement to give us an idea of what a random variable is like. Well, now we're interested in a random variable, which is X minus C squared. That's the penalty. And that's still a random variable. So it's a function of a random variable, so it's a random variable. And so the best we can hope to do is to minimize the expectation of that. The perfect case would be that we predict X perfectly and we have an error of 0 and we'd have a loss of 0. So we take the expectation of that. So expectation of this quantity, X minus C squared. This is called the mean squared error. So we're taking the mean, the expectation. I don't think I mentioned that last time. The expectation is sometimes also called the mean. We're squaring the error, right? So the error is just the difference. And sometimes that's also just written as MSE. And the root mean squared error is the square root of that value. And the reason we take the square root is that it puts the error, the error on the same scale as the original random variable. So for calculation purposes, the root or not the root doesn't really make a difference because it's very easy to just add or take a root off. You take the root off by squaring this root mean squared error. But for interpretation purposes, it's important because it puts the error on the same scale. What do I mean by that? So suppose if X is measured in, we'll say inches, then the mean squared error is going to be in terms of inches squared, right? Because mean squared error is X minus C squared. So it really depends on X through the square of X, and X is inches, so X squared is inches squared. So the square root of the mean squared error is measured in square root of inches squared, which is just inches. So it's back on the same scale. And that's true of any measurement. If we wanted to do this in terms of pounds, this would be pounds squared, this would be pounds, etc. Okay, so the question then for prediction is, what C should we choose? In other words, what is our best choice of C to predict X to minimize the root mean squared error? And for this, first of all, let's just define mu to be the expectation of X. That's a common notation that we're going to see throughout the course. Mu is often, it's a Greek letter mu, Greek letter for M. It's used for the mean. So we've talked about mean and expectation. They're the same thing. And we do it here for simplicity because E of X just takes up a lot of space when we're trying to write this. Now, when we do this, let's realize that the variable, the penalty, the error, the squared error, X minus C squared, what we can do inside of the square is we can add and subtract mu. So we haven't done anything, right? Because all we've done is we've added a mu and we've subtracted a mu. So that's a net of 0. So we've done nothing significant here, done nothing new. But then we can group things this way. If we group things this way, what happens? Well, we expand a binomial. So we expand it in terms of these two groupings. So what we're left with, what we have is we have x minus mu squared plus the cross term, which is 2 times mu minus c times x minus mu plus mu minus c squared. So this is just now a nice, another way of writing x minus c squared. And we're interested in in minimizing the expectation of this x minus. We're actually interested in minimizing this, the root mean squared error. But we realize that we can minimize. So to minimize the root mean squared error, it's enough to minimize the mean squared error. So I mentioned that for calculation purposes, it's really often easier to work with the mean squared error. We don't have to carry around this square root. So that's actually what we do work with here, because to minimize one is to minimize the other. Why? Because as a function of c, these variables, the mean squared error, the mean squared, these values, the mean squared error and the root mean squared error, are minimized or maximized at the same place, because mean squared error is an increasing function of c, root mean squared error is an increasing function. Well, it's a quadratic function of c. They're both quadratic functions of c. And so they both are, and the root mean squared error, of course, can be obtained from the mean squared error by just taking the square root. And the square root is an increasing function, so it's a monotone function. So we can take so it's enough to minimize the mean squared error. So let's do that. So we take the expectation on the left, we take the expectation on the right. Now, first thing is we have this quantity here, which needs to be, we need to take the expectation of. Remember, the additivity property of expectation allows us to break this up into 3 terms. So we can, the expectation of these 3 terms is the sum of their expectations. Okay. Copy down the first term again. That's fine. This middle term, we have a 2, which is a constant, and we have a scaling property of expectation, so we can take that out. We also have mu minus c. Mu minus c is also a constant because mu is a constant. Mu is the expectation of x. C is assumed to be a constant. We have to choose what it is. So we can pull those out by the scaling rule, and we get expectation of x minus mu now. And then expectation of mu minus c squared. Mu is constant, c is constant. The square is just a constant function. So this is actually just mu minus c squared. You can pull it out of the expectation. And then you would be left with expectation of 1, the number 1. We haven't discussed this, but the expectation of a constant is a constant. right? That should be pretty intuitive, and that actually is how the math works out. A constant is just what it is, right? It's always itself. So you could think of it as assigning probability 1 to a particular value. If you assign probability 1 to a particular value, you calculate the expectation, you just get the value back. Okay. All right, what's next? What's next is realizing that the expectation of x minus mu, we can apply the additivity rule again here to say that this is expectation of x minus the expectation of mu. But what's the expectation of mu? Because mu is just a constant. So what's the expectation of the expectation of x? It's just the expectation of x. Again, expectation of a constant is the constant. And so I can get rid of this expectation. But then what is mu? Mu is by definition the expectation of x. So this is expectation of x minus expectation of x. This is 0. So this term here is just 0. It's something multiplied by 0. So what we're left with is the expectation of x minus mu squared plus mu minus c squared. And this is the function that we want to minimize, and this is a function of c, right? So we want to minimize it as a function of c. Nothing else, that's the only variable that we have at our disposal when we predict x. So let's call this something f of c. And to minimize, there we go. Minimize f of c, take the derivative. With respect to c. So what is it? Well, the derivative of f with respect to c, what's the derivative of this first term with respect to c is just 0 because it doesn't depend on c. The second term is quadratic, so it's -2 times mu minus c. So let's set that equal to 0. And then let's set this equal to 0. And if we do that, what we find quite easily is that c needs to be equal to mu. And then to confirm that this is a minimum, we take the second derivative with respect to c. We see that it's equal to 2. That's positive. That means that c equals mu. Minimizes f. Okay. So that implies that the minimum root mean squared error of prediction in this case is given by what's called, we'll write it as sigma x. It's also written as SD of x. It's the square root of the expectation of x minus the mean squared. Which is called the standard deviation. So the standard deviation, so what have we learned here? So what we've learned here is a few things. Well, let me just finish here, which is that the variance, which is the square of the standard deviation is we just take the value of the standard deviation, we square it, we get rid of the square root. This is called the variance. Okay. So what have we learned? What we've learned is two things. Well, at least two things. We've learned a little bit about how to minimize functions and how to solve this prediction problem. We've learned some intuition for what the mean actually does. The mean is our best guess, the expectation. It's our best guess at a random variable if we had to guess with one number. That would be, the mean would be our best guess. In what sense? It's our best guess in the sense of root mean squared error, minimizing root mean squared error. So if we minimize something else, we might have a better guess for something else. But if this is our error, if this is how we judge our guess, our prediction, then the mean is minimizing. It's the unique minimizer of this this value, this error. And the variance and standard deviation are the minimum possible values of this prediction error. So they are telling us this is the best you can possibly do at predicting this variable, this random variable, by a single value on average. And so that's that's what's telling us in some sense how erratic or how unpredictable the variable is by saying that the best you can do on any given, the best guess is the mean. And this is what the value is. This is what the error will be in the case of the mean on average. And you can't do any better than that. So that's what mean, and that's what standard deviation and variance are. And we're going to talk about how to calculate this. We're going to derive a good formula for calculating this and go through several examples.